Hello, Atul sir, it's over to you. You can start. I'm making you host.
Hello everybody, good morning.
Good morning.
So I request all the participants to keep their mic muted. I mean, if anybody will keep their mic unmuted, if there is some sound, we will not be able to get the meaningful outcome from this. I request all. Okay, and please make sure that your mic is muted. So let me start today's topic. So I believe you all can see these slides. Can a couple of people confirm?
Yes, sir.
Visible.
Yes, sir.
Okay.
Yes, visible.
Oh, thank you. Thank you. And keep your mic unmuted again. I request all the participants to have a fruitful session this session. So again, very good morning to all of you.
Good morning, sir. Good morning, sir.
Good morning. Good morning. So now please keep your mic unmuted.
All the participants, please keep your mic muted, please.
Okay, so this session is going to be. So please don't raise any hand at this point of time, right? I request all the participants to not to perform any activity until.
Good morning, sir.
Good morning. Good morning. Until unless it is required.
Hello.
Sir, please little bit louder. We are not getting you.
Good morning, sir.
Your voice is not
Good morning,
clear,
madam.
sir.
I think I have had all the setting right. I don't know if.
Sir, you please in.
They need. Hello. Can you hear me?
Sir, you are audible. Please continue.
Yes. So I think for my side, the sound is loud and clear. And if somebody is not able to hear, please check their settings, sound setting. Is this clear? And I will.
Sir, all okay.
So I request all of you.
Able to hear you, no problem, sir.
Thank you, thank you. So now I request all of
Sir,
you.
please continue. Please continue, sir.
Yeah, I can continue if I would be given some freedom to continue. So I request I should not be disturbed until unless if somebody want to ask any question.
Okay, sir.
So there is some Sajian R.K. Verma and his mic is not muted. So I request all of you to keep your mic muted. I mean, see, this is an online session and it is very important that you cooperate. Otherwise, it will be disturbance to all of us. I still see that some of you, somebody is has not keep.
Sir, I sorry to interrupt, sir. Sir, I request you to please mute all the participants.
Good morning, everyone. We are at the start this session.
Sir, good morning. You have also a facility of unmute.
Yeah, I'm keeping all the participants muted. So let me start.
Presentation.
And again, what happens is some people will join and they will keep their mic unmuted and there will be again some issue.
Remove such participants, sir, if they are disturbing.
I mean, I can do one thing right at a time. I cannot pay a lot of attention to each of you.
Sir, please continue. I'll coordinating with you.
Right. So this session, again, I welcome all of you to this session, which is going to be an introductory session for machine learning. My name is Atul Gupta, and I'm an associate professor and head of computer science in the department at IIITDM Jabalpur. I'm also serving as an associate dean and convener to computer center of our institute. Regarding my PhD, I did my PhD from IIT Kanpur in 2007 and 8. And my research interests include machine learning, um, data science, software engineering, NLP. So those kind of things and I'm interested in the machine learning stuff. So I believe that this session is going to be useful for all of us. I got some 40 good publications in reputed journal conference, and I have guided as of now 8 PhDs and 20 MTech students. I'm also serving as a co-PI of ICT Electronics and ICT Academy at IIITDM Jabalpur and a co-coordinator for Design and Innovation Center at IIITDM Jabalpur. So this is just a brief, and if you would like to know, just ping me, mail me, and I will let you know more information. So the first question that should come in our mind is like, why machine learning, right? So for this, probably, or many of you now know this answer, that there are some problems, or many problems in fact, that they are very hard problems because for which we don't know how to write program to solve those problems, right? I'll take this straightforward this case. You see this is the paper, one paper which is appeared just 4 days before, which is published in Nature Machine and Intelligence. It's a highly reputed journal. And this is published by Chinese author. Yeah, so the name of this paper is, you can see this, an interpretable mortality prediction model for COVID-19 patient. And obviously, this paper is published by, can you please keep your mic muted?
Newly joined participants, please mute your mic.
Okay, so this paper, which is recently published, right, is titled as is an interpretable mortality prediction model for COVID-19 patients. I can tell you, right, this is a work based on machine that what is the chances a person is going to be alive after some time. So these patients have been diagnosis, and this and the authors, they belong to Chinese, they belong to China, and they have collected data from hospitals of Wuhan. And you see that this is published very recently. So I'll come back to this a little later, but just try to suggest that there are a number of applications where the machine learning can really make a lot of difference. Right. If you are more interested, I'll again come to, and I'll show you that how other applications of fighting COVID-19 can also be handled by machine learning. So this is just an introduction part of it. So again muting them. So that is a continuous operation that I have to actually ensure, and there are number of participants still getting admitted, and some of them, what they do is when they join, they keep their mic unmuted, and that's great. Anyway, we are new to this, I think this kind of arrangement. Generally, we are not used to of like online classes, which is carried out in real time. So we will be learning certainly, and gradually we will know that how to like make sure that yeah, we are participating in a useful exercise, right? So still some participants are getting entered and no issue. So again, the question is like, why machine learning, right? So can you see this picture here? And the problem is that can you identify the objects which are given here in this picture? Now, at the same time, you need to think about it that when we try to write a program, see, this is an image, and how do you read an image? By like pixel by pixel, so you can read this image, which is nothing but array of pixels. So it's a mostly two-dimensional array where of some size, and we can, and people are keep coming like entering in this. That's the problem. I guess we have to learn this, that all of you should join much before then we start the session, and yeah, that's the problem. Anyway, so you can see that what are the objects in this picture, and as far as the human eyes are concerned, they are straightforwardly can determine that these are the objects, and there are some bottles, a cup, or a packet. So those kind of things are already there, and we because of our eyes, we can quickly figure out that what these objects are. In fact, we can figure out all this about all this image, and we can describe this image very efficiently with full like detail. But what about the program? If you want to write a program, can you write a program which can take this picture and can identify all these objects and can describe all of them with all those gory details? Just think about it. If some of you might be enthusiastic enough, then I invite you to write a program which can take this image and can identify what are the objects in this picture, right? So this is one problem. You can see the other problem like self-driving car, autonomous vehicle. So what autonomous vehicle will require is like when they are on the road, they will be facing what are the other objects in the road, right? And they need to know about their position and how they are moving. So these information are very important. So again, if we think about that there is an autonomous vehicle on the road, certainly it is going to have some cameras, right? And these cameras will be live streaming about this data, about the scene in front of the car or truck or whatever the vehicle, and it is continuously identify objects from this streaming data. And this is important, right? You know that this has to be done. Otherwise, how can we have a driverless car, right? See, when you use your card and you believe that your card is going to be safe, right? So you draw money from your ATM or you perform some online transaction using your credit card. And what you want is like your transaction should be safe. So how do you detect that a transaction which is being performed can be a fraudulent one, right? So it's not a straightforward idea. Just think about it. Whatever the examples I am giving to you, just think about it. Can you write a program? Can you write an algorithm which can take whatever input you think that you would like to take, and can you process them, these inputs, and can determine that, for example, this transaction is a fraudulent transaction, so that you can stop that at once, and this is how you can take care of these fraudulent transactions, right? Another application is like, for example, people across the globe, they used to speak different languages, right? Now, how would it be possible that whether you know their language or not, still you are able to communicate? So it's about like language translation. So you speak one language, and there is a device which convert that into another language. For example, your mobile. Nowadays, this mobile is already doing this kind of job. That somebody speaks Chinese, he will speak Chinese in front of this mobile, and this mobile will convert this translation, will convert that into, let's say, English or Hindi, right? Again, there are people still keep coming, and I am inserting them in this conference, and also I have to mute them. So please bear with me. All of us need to understand that yeah, this is a new idea to have these kind of virtual conferences and to join these conferences and to make them successful. We have some role from our side, each of us, to make sure that yeah, this become a useful exercise. Okay, so one thing is you always join in time and keep your connection, which is like a good connection. So if you are not having a good connection, so what may happen that you can keep on disconnecting yourself, and then you would like to join again and again. And what it is going to create a problem, like whosoever is coordinating, he has to continuously like ensure that okay, people can join at their will, but then if some participants have their mic unmuted, then they will create further problems. So go for a good high-speed connection, whosoever can do that. Okay. So language translation is another example. One more example is like when you read a piece of text which is written in somebody's handwriting. So how do you do that, right? So as far as, again, human eyes are concerned, they are very capable instrument. They are very capable tool. It's very hard to have we can design something which is close to human eye. But still, one of the problem that we can think of solving is to recognize handwriting, and some piece of text written in somebody's handwriting what is written in this, right? Okay, so let's go ahead and yeah, just like you can give some commands. So like Google Assistant, which can take your commands in natural language and can do job for you. So those kind of personal assistant, they are also like the kind of programs which you will find that they're not very simple to write, right? So how can you design these kind of applications? I mean, you can successfully have these applications running on your systems, on your mobile, and you are able to get the things done. One interesting application is about like share market price prediction or share market index prediction, right? And many of us might be sometimes very curious about that. Can we know about that which share is going to get high today and going to get low? So if we know this information, then we can make a lot of money, because as it goes high, we'll sell those stocks, and if it goes low, we will buy those stocks. So companies across the globe and people across the globe, they are trying hard to know about that. Can we predict the same market price a little advance? And it's a very challenging application. And you know that if somebody has even a more than 50% accuracy, then this person can definitely make some good money, right? But again, I can tell you that this is not a simple job, right? So keep on thinking that how these applications can be programmed if you want to program, right? Spam filter, for example, a very simple example and a quite old example, but a very good example of like how the mails that you get is mostly they are legitimate mails, and all the spams which were directed to you are not figuring out in your mailbox, right? So you know that there is a program called a spam filter, which is deployed on the servers. For example, if you are using a Google Mail, then that is deployed on a Google server, and it is doing this job for you, that you don't get spams in your inbox. And at the same time, if you want to know that what mails were targeted, what spams were targeted to you, you can go a spam folder and can see that all those spams. So how come a program has done this job for you? So again, can you think of writing this program? And then there are many other applications. When you type in Google, then you get some recommendations, right? So what string you would like to type. So in fact, there is some kind of assistant which is given to you that can you formulate your search string in a more correct way, so that you can get the information that you were looking for. So you can see that how this is possible, right? How, and there are other recommender systems like when you buy something on your eBay or Amazon, and you get some recommendation, which probably some of you you would like to go for them. So how it is happening that how this program knows about you, how this program knows about that what you require. So that is very challenging and very interesting programs, right? This is the Google car, driverless car. This project was started in 2015, and still continue. I can tell you, like, people initially thought that this problem, though complex problem, can be solved with some good amount of effort and money, putting some money into it. But after some time, they realized that this is even harder problem than the problem that they initially envisioned. It's a very challenging problem. And there are many countries across the globe which are trying these autonomous vehicles to be on their road. One important motivation behind having these autonomous vehicle in road is not to reduce the job, but rather than reduce the number of accidents. So it is quite understanding and it is believed that when this vehicle will be on the road, we can drastically reduce the road accidents. Right. What about the India? Yeah, but we haven't even started thinking about it. That is it going to possible for our roads to have these driverless vehicles? Very interesting, right? So that's why there is no project which is funded by the government, which is running and which is trying to figure out that can we have driverless car on our road. So for now, we are not going to have driverless cars in our road. Just think about this driverless car. So how it does the job? I mean, like any other driver, the driverless car needs to know about continuously and constantly figure out that just a minute, hold on. Still some people are getting inserted in this conference, so I'm adding them.
Sir,
Yeah, please.
hello.
Yes.
I'm
Yes.
coordinating with you, sir. So I'll do that.
No issue. Okay, just
Okay.
do that. And people are requesting, so
I'll add them, sir.
Okay, so just think about it. I mean, how a driver can think and will act while driving the car. So if you want a machine to do all these kind of things, so the machine has to be that much smart, that much intelligence to understand, to figure out that where this car is, what are the objects around this car, what is going to happen next, and what this machine is going to take a decision here, right? So very interesting problem. And I can tell you there are many countries where the driverless car has been allowed to go on the road. And this is just one example which is shown here in this. So the question is like, why machine learning should have motivated you if you already know that why we solve why we need machine learning. But if some of you still like wonder that why we need this fancy stuff, can't we solve it in our traditional programming way? So I'm giving you this more detailed and more simple example just to know about that. Can we identify digits which are written using hands, right? So hand written digit recognition, a very simple looking problem, that can we identify this hand written digits. So there are only 10 digits, 0 to 9. And you can identify, so your identification problem is about only identifying these 10 digits. So we are keeping our problem simple. And what we can even assume that all these digits are written in the same like place, so same size place has been used to host these digits, right? So these are the simple assumptions which will make our life simple. So just think about it, since these digits are written on a piece of paper, and how we are going to read them or recognize them is we are going to take this just first of the picture of it and take the input. So how we are going to take input of these digits is like is in the form of images. And you know these images are nothing but a grid of pixel. So let us assume a simple grids where these images can be captured, right? So maybe like 16 by 16 grid, 16 by 16 pixel. And you can see like these handwritten digits will look like when they will be. Deepshika, Dr. Deepshika, if you can
Yes, sir.
disable the screen share option. I mean, the participants are drawing some, yeah, so that they are interesting participants. They always let us know that they are present in this meeting. So,
Okay.
so there is a setting where you
Okay,
can
sir, I'm
write
checking.
annotation. So there
Yes,
is
yes.
yeah, so you can disable the annotation, and that will make life of most of
Okay,
us.
sir, I'm doing that.
As I said, I mean, we have still some way to go to learn and to understand that how online class can be successfully carried out. Online sessions can be carried out, right? You see, in near 1 year, I mean, most of the conference is going to be online conference. So why? I mean, this is where you will be joining. So this is all going to look like the same way as we are looking here. So yeah, I consider it like a fascinating stuff that I because I've been using it for quite a while. I know that there are a lot of advantage of also to use this mode, and that should help us to better delivery and better exercise in which we spend our time, right? So just think about this digit recognition problem. So can you let's say for example digit 4. So can you identify this digit 4? Can you write a program which will read pixel by pixel and can suggest that this image consists of 4, right? So I'm keeping this problem very simple. Forget about like we are identifying if there are some object on the road, and these objects can be a whole variety of which you even cannot figure out in advance. So, but then we know how 4 looks like. So, can we write a program which will identify 4, right? So, one idea is like simple idea is like reading this pixel one by one, and then we can figure out that some of the pixels are going to be dark. If it is, let's say, binary image, then then it can be like just black and white. So some pixels will be black and some pixels will be white. We can figure out, we can have some kind of like if then else statement, that if these pixels and these pixels and these pixels and these pixels, I mean, we can write a horribly complex logic where we can figure out or we can conjecture that if these pixels are dark, then and the rest of the pixels are white, then this image is 4. I mean, just think about it, how simple this idea is, right? But you know that 4 can be written in many ways, right? So when the 4 can be written in many ways, can you write one deterministic if then else, howsoever complex logic to identify 4 from an image, from even a small image, right? So it's a difficult problem. Probably by this time you should have understood. Right? So coming to machine learning algorithm, yeah, we first see a classification of machine learning algorithm, and then we'll look a few important algorithms, right? Yes. So you can see that the machine learning algorithms is divided into primary 3 categories. One is like called supervised machine learning. The second category is unsupervised machine learning. And third is like others, which mainly includes like reinforcement learning, right? So supervised machine learning is again divided into, or there are 2 kind of problems which falls under this category. One is called regression problems or regression learning problems. And the second one is called the classification problems. In unsupervised, there are clustering problems, association rule mining problems. And as I said, in other category, there are the important algorithm that falls under this category is reinforcement learning. And so the task that we will be taking in this lecture is like to introduce some basic algorithm for supervised machine learning. And as you know, that supervised machine learning has 2 types of algorithms. One is regression algorithms and the other one is classification algorithm. What is the regression problem? Regression problem is about predicting or computing a real value attribute or real value answer, right? So the difference between the 2 types of supervised machine learning problems like regression and classification is, in one case, we tend to learn and therefore predict a real value attribute, a real value number, right? Which is going to be like, for example, here what is going to be the score of the today's match, and how much runs India is going to score. So if we want to predict this, if we want to know about this, then this is a real number, right? And the classification problems are the problems where we find that there are few finite number of predetermined classes to be predicted about. So it's not a real number. It is not going to vary. I mean, what we know about it is like there are fixed number of outcomes which are possible. For example, sentiment analysis, where there can be 2 sentiments. One is, for example, a positive sentiments and negative sentiments, right? So, or it can be 5 kind of sentiments. So if we know about these classes in advance, then these problems are, they fall under supervised machine learning, and that too like classification problem. Regarding clustering, so the clustering problem is like when you have some data, you want to create some clusters, right? Clusters are nothing but those data points which share some similar properties, right? So for example, in this image, we want to know some section of this like brain which which can be treated as an object, right? So maybe if like a brain cancer, brain tumor, so we would like to identify, say, what part of this image constitute that tumor, right? So this is nothing but the grouping those pixels to identify that tumor. So clustering. Another problem that falls under unsupervised learning is like association rule mining. So many of you have done the course on like data mining. They are familiar with this famous problem like market basket analysis, right? Where you would like to know about that which products are sold together, right? So those kind of things, that if there are number of objects, how these objects are associated. So can you figure out the association which might be there between the objects? That's why the name of this algorithm, this kind of algorithm, association rule mining. And then we have reinforcement learning algorithms where we learn while we do it. So in this kind of problem, which is different than other supervised and unsupervised, is that we probably don't have any data upfront, but what we do is like we start taking actions, and based on our actions, whether we get a good reward or we get some kind of penalty. So based on this rewards or outcome of our action, we learn gradually. So this is more close of like how human, they used to learn things from scratch, right? So they start doing something, and then they will know that, okay, by taking this action, they got some favorable results or they got some unfavorable results. And therefore they will remember this kind of information, and gradually after a number of like actions, their experience will go up, and this is how we will term them as like they have learned something. So this is about the reinforcement learning. So today's topic will not include unsupervised or reinforcement learning. What we're going to discuss is like supervised machine learning, and we'll see one algorithm for both regression as well as classification problem. Right. So if you look at, I'm going to discuss like now regression learning and classification learning, and we'll see some applications of regression learning so that we are more familiar with the regression problems. And then we will also see some applications of or some problems which falls under classification learning. And then once we are familiar with this regression and classification problem, we will see that how we can solve these problems, right? So I'll take one algorithm on each of them, but then there are many other algorithms. So I hope that some of them will be covered in the following courses. But the idea of like how regression learning work or how classification learning work should be clear to me. So first, regression learning, I mean, an important application is like weather forecasting. So you would like to know that what is going to be like the weather tomorrow. So what is going to be the temperature, the minimum to maximum, right? And what can be the wind speed and all that. So you can see that these variables, temperature or wind speed, these are the variables which are continuous variable or real number attribute, right? So that's why, as I said earlier, that regression learning, we try to learn a variable which eventually we are going to predict. We are going to compute the output of this variable, and these variables are real numbers, right? Real values attribute. So for example, weather forecasting, share market prediction, you know that like index, share index is like a real number variable. And that's why this is falling under regression problem. This autonomous vehicle. So you know that how much you need to turn the vehicle. So angle of like of the steering, right? Or you want to push brake or you want to push accelerator. So those kind of like signals or eventually the values are going to be real numbers, right? So that's why this, again, these kind of problems, they are falling under regression problem. Yeah, please mind that in this autonomous vehicle, there is no single regression problem. There can be a number or a set of regression problems that is to be solved. Each of them will be solved, and they will cooperate and collaborate in some fashion, these solutions, to ensure, to run this vehicle. So those kind of things are there. And there can be some classification problems also that need to be formulated and to be solved. So this is really a complex problem in autonomous vehicle. but I don't want to go into those kind of complexity for now. Just keep things simple for the people considering that this is introduction course to machine learning. Okay. For example, when you code, right? So coding, so how many bugs a code can be, right? So finding or predicting that this code is buggy and how many bugs can be there in code. So this is also a problem, which is regression problem, right? Similarly, land profiling, computing the soil properties, for example, moisture in the soil. So those kind of, again, problems will be regression problems, right? Monthly cell predictions also, I mean, this again, there are some numbers which are involved, and these numbers may vary from some minimum to some maximum. And if we talk about like cell cost of the cell, then this is like, again, in terms of like dollars or rupees. So if you want to estimate about this prediction, estimate about your cells in terms of like money, so you know that this is a regression problem. So I think I have given you enough number of example, cricket score or match score. So again, this is like a regression problem. Let's go to a few instances of classification problems so that we can differentiate what is regression problems and what is classification problem. So for classification problem, as you know that we should have a few number of finite predetermined classes to figure out in our problem. So for example, sentiment analysis. Now here in this case, like there are three class. One is negative class. And so let's say you want to give a review for a movie, and you want to rate this movie as a positive or as a negative, or you say like you don't say anything, right? Or you say it's okay, so and so. So maybe you're neutral about, right? So you got three classes here. So that's why this is a classification problem. When you deal with few number of finite classes, and they are already known upfront. This is important thing. Important to discriminate between classification problem and a regression problem. Spam filter, and given a mail which is spam or non-spam. So again, there are two classes. Either the mail can be a spam or can be a non-spam. So we know that there are two outcomes. So that's why it's a classification problem. Will it be rain today? So again, we are going to answer this problem as yes or no. So again, it's a classification problem. But if you want to measure the amount of rainfall, then that will be not a classification problem. That will be a regression problem. So I hope this you understand this discrimination, this distinction between classification and a regression problem. Now, another problem like who will win the title. So you know that you have fixed number of or finite number of teams and they are fixed. And we need to know about that who is going to win the title. So again, this problem, though there can be 10 teams, there can be 20 teams, but we know them upfront, and therefore this problem is a classification problem. That if we are going to name that Arsenal or Manchester United is going to win the title, right? This is a cancerous image, and this is a mammogram basically, and we would like to know about whether this is a cancerous one or this is non-cancerous. So you see, again, it's a classification problem, or it can be three classes like it's normal, it's a normal means this is just a normal stuff. It's happened to everybody or most of us. Benign is like it's a lump, but it is a benign one. I mean, it is not a problematic, though it is a lump. And malignant is like that lump may be a cancer, right? Cancerous one. Similarly, if you're given some image and you want to identify objects from this image, like let's say image of a dog, and you would like to know that whether it's a dog or it's a lion or it's a cat. So you know that you can figure out you're going to label them with fixed number of labels which are known upfront, and therefore this is again a classification problem. So the general idea about supervised machine learning, I mean, both classification and regression is like we learn from data. So machine learning is basically an idea, a way of solving problem where we don't write an algorithm upfront and then pass on data where the algorithm will work on the data and will provide us an answer for it. It's not like this. Rather than in machine learning, what we are going to do is we are going to program using data. So the data is a first requirement for machine learning problem. More importantly, supervised machine learning problem, right? Whether it's a regression problem or classification problem, you require some kind of data. Now, why we require data? Because this data for supervised machine learning, they will have not only the problems as well as their solutions, right? So this data is going to be comprised of the problems and solution. So one instance of problem and the solution, the second instance of problem and solution, and third instance of problem and solution. So this data is going to comprise of labeled example, which is, in other words, we say that examples, learning by examples. And these examples have been solved examples. If they are not solved, if we don't know their solutions, then these problems will not fall under the category of supervised machine learning. The name of that we use supervise is about there is a supervisor, right? Which tells that this problem has got this solution. This problem has got this solution. So when we know multiple instances of problem which have been solved, so in some sense what we are trying to do here is that we are going to capture this relationship between the problem and the solution, right? So it's going to be more of a mapping where this is the problem and this is the solution. So from this pair of problems and solution, right, ordered pair, problem and solution, and many of them, we'll try to generalize this idea that from the existing set of examples where we got these problems and solutions, can be learned, can be understand, and it's not a difficult idea to understand that we also see that we have solved some problems, and just in our mathematics course or physics course or whatever course you've done, you have solved some problems, right? You've given some problem, one problem you solved it, you know it's how to solve. You got second problem, you know how to solve. Third problem, you know how to solve. So given a number of problems, maybe hundreds of them, and you know that how to solve them. Now if I give you the next 101th problem, which you haven't seen earlier, but probably because you have solved these 100 problems and you know how they have been solved. So based on this problem and solution relationship, right? There is some connection between the problem and solution. You use this idea, which you already acquired in your mind. So your mind is already trained that given a problem and its solution. Please differentiate the learning from memorization. That is another thing can be that you got 100 problems and you know their solution, right? And what you did is you mugged them up. So given that problem, you know, because it is in your memory, so you can face that because you have seen the problem, you can get the solution from your memory. You see in the next problem, you can get the solution from your memory. But when you see a problem which you haven't seen earlier, obviously its solution is not there in the memory. So obviously you're not going to solve it. You're going to say that, okay, I cannot solve. But this is mugging. This is not learning. What I'm talking about learning, that given the problem and its solution pairs and a number of them, we try to figure out that what is the connection between them. What part of the problem which modeled in a step-by-step way to get the solution. So you learn the pattern of solving that problem. And once you are good at solving them, so even if I give you a new problem, you're going to solve most likely you're going to solve it. That is what the learning is in our sense also. And that is what the learning in the supervised machine learning sense also. So for each specific problem, what we are going to do, we are going to collect a lot of examples with their known outcome, means their solutions. And then my program that I'm going to write will take these examples with their solutions and will try to learn a function that will map inputs, problems to solution, right? So this mapper is what we are actually going to figure out from our learning. So if we can identify this mapping function, if we can derive this function, and that is how we solve this problem using the machine learning way, supervised machine learning way, right? So I believe that at this point of time, you probably understand the difference between the traditional way of solving problem and the machine learning way of solving problem. Machine learning is learning from data, right? So you need to have data, and a lot of them. Gradually you will figure out that when you go and use some very sophisticated algorithms in deep learning, you need much more data. And why deep learning is getting popular is because nowadays there is no scarcity of data. Data is plenty. It's generated on a minute to minute basis, on a second to second basis, and on a daily basis. So we have got hold to a lot of data. And that is a win-win situation with the deep learning solutions, that they require also like a lot of data. And therefore, with a lot of data, they can learn some very, very complex functions, and their performance can be very high compared to the traditional machine learning approaches. So deep learning algorithms are even the advancement that has been made in the field of machine learning. And therefore, most of the problems you will find now there are deep learning solutions which are taken over rather than the old machine learning solutions, right? But that I leave it for later. And obviously you will explore this idea and you will learn about them also. But the fundamental remain the same, right? About the machine learning, the basically learning problem. So let us come to a general formulation of a supervised machine learning problem. And as I said, this supervised machine learning problem can be a regression problem or a classification problem. So for now, I may take one of them, but please note that the other formulation is also relatively straightforward. Okay. So the generalized supervised machine learning task is what we are going to do. We are going to have access to data. Now that data might be a raw data. For example, it can be a voice data, or it can be images taken from a camera, or it can be like videos, right? Or audio. So it can be any kind of data, which is like in the very basic form where you capture this data, right? Now what you do in typical supervised machine learning task is you extract the features from this data. Since data is raw, so the data is to be made in some presentable form. So typically what we do is like we identify a few features, important features in that data, and then we store these features, each of them. Let's say we identified 10 features. So what we are going to do, we are going to store all these 10 features for each instance of the data, right? So you got like, if let's say you got 1,000 instances of data and you extract 10 features, so it is going to be more or less like 1,000 into 10 kind of table, a two-dimensional array where we can store these features, right? So the features, if you have heard about, is nothing but the data that you extract from the raw data, right? Otherwise, your raw data might be a little difficult to handle directly. But later on, you will see that there are algorithms which directly take the raw data rather than extracting features, and they can directly use this raw data and can get the job done even more effective way. And again, the deep learning, what I'm talking about, like the deep learning algorithms, which can even deal with the raw data. And that is another advantage of using deep learning, is like you don't have to bother about the features, right? They will learn their own features, and they will probably learn even better features. So when you go and extract features, somebody has to take a call here that what features is to be extracted. And therefore, for the same problem, if one person extract, let's say, some features, the another person extract some other features, definitely these features, this set of features, going to affect the performance of the learning algorithm. So it is important when you use a feature-based learning algorithm, then the feature set is going to matter a lot. So you have to put a lot of attention to your feature set. Anyway, when you extracted these features, then these features, along with like the data which is labeled. So feature represent the data, and there will be label. Label is nothing but that will make it like a label data. So feature represent the problem, and the label data represent the solution. So we have got this feature and the label. The second set of features and the label. For each of the instances or each of the data point, we will have the features and the outcomes, the solution. So that is denoted by a single column here for now. So you can understand that all these features correspond in a particular row. We are targeting one instance of the data, and all the element of in this row except the last one represent the input data, that is the feature vector, and the last element in that row is the label data, right? Because we are learning from label data, solved examples. Supervised machine learning from solved examples. The solution is the last column where the solution is written for this problem. Now this data is given to a model, a learning model, a learning algorithm. Now this here you need to understand, right? What does it mean by learning algorithm? So there may be a number of learning algorithms you'll come across, and you have to choose one of them. For example, here as it looks like in this slide, it's a neural network model, right? So you are using a neural network. So what is the purpose? The purpose is to feed this data as a training data and to this model, which is initially untrained model, right? So this model is a bare, like untrained model. This is the neural network. And somebody is helping me, that's great. So what will happen after this exercise? The label data, when is provided to this neural network, this data is going to help this neural network to learn. Now, how this helping will be done, how this neural network will be helped by this data, is that these edges will carry some weights, right? So I believe that when you will go and learn about neural network, you will know about that, how neural network, that is a network of nodes, and they are connected with through edges or between these set of nodes, and each of these edges will have some weight, right? Initially we'll have some random number weight, and this data, which is the label data, will allow us to adjust these weights and in an iterative fashion. So once after a number of iteration, we'll see that what does it mean by iteration. We'll go from left to right. We'll compute some activation function on each of this node, and then we'll compute the error at the end. And if there is an error, then this error will fed back in the system in the backward way, and it will, while it is propagating backward, it will be adjusting the weights of each edge. And this is how these edges will be, edge weights will be adjusted. And once we do it a number of times, and when it converges, so I believe that these terms will be more clear when you will be exposed with the neural network. But the whole idea is like this label data is making this network to learn. And the learning is nothing but the adjustment of the weights, knowing about these weights between these nodes, right? So the ultimate learning is like the age weights are finalized, and we will call that as this model as a now learned model. So we got this trained, right? And once this is trained, now what we can do, we can give a new data, the data which probably not encountered earlier. So again, in the same way that it will be a raw data and its features will be extracted. So in the same form as the way the label data was given for training this model, we will formulate our query instance in the same way, and this will have this part as not known, right? So you can see a question mark here, and this question mark is nothing but the label of this this query instance that we would like to know. So did you get this supervised machine learning problem? Is like we got initially a number of like data points where we got a number of data, for example, and then all of them were having the labels, right? So that means that we got the problems and as well as their solutions, and not just one single problem and solution, but number of problem instances, I would say, and their solutions for that instance. So that is nothing but the data for learning. Once we got our model trained, that is the way we got our model trained, right? And then what we are going to do, we are going to take a new test data, which is nothing but not categorized on unlabeled data, whose features are known, so that can be extracted the way we have extracted the features of the labeled data. And then for this part, that is the part that we would like to know the answer of this problem, this we will pass this data to this learned network, and this learned network is going to provide us the answer for this problem. So this is how this whole process is going to look like, which is called supervised machine learning, right? More formally, we are going to see that here in this formulation we are discussing a classification problem, but then the same is applicable, similar thing is applicable for a regression problem also. So what this problem is, a classification problem with known k number of classes, right? Okay. So in the classification problem, what do you know? That we know upfront that how many classes is there in this problem, so that we are going to predict one of this class for a new query instance, right? So what is the input for this this kind of problem? A labeled data set. This I already told you, a labeled data set, and this data set is going to consist of an ordered pair of type X superscript 1, Y superscript 1, X superscript 2, Y superscript 2, and so on and so forth. So what it indicates that there are M data points and M examples, and for each examples we got X1 and Y1, X2, Y2. Please mind that we are using superscript here because we are going to use subscript for some other concept. So superscript is about, they denote the number of data examples, right? So X1, Y1 is like the first example. X1 is the problem. It will be nothing but a set of features. So it will be a feature vector actually, right? And Y1 will be a label for that particular instance. Similarly, X2 and Y2 and X3, Y3 and XM, YM. So what we are assuming that there are data points which we will be using for training the classifier or training the algorithm, right? So where each xi is a feature vector defined over a features. Now, here comes the subscript, right? So the feature set will have some n number of features, for example. So x1, x2, x3, where we are using them, this 1, 2, 3 in the subscript. These are nothing but they are features, right? And consider that there are n features, right? Well, I'll take an example, so those things will be even very clear to you. And yi is the target class, right? So that is the input, and one more input that we are going to give is nothing but the query instance. Once you got this training is done, then you are going to provide a query instance xk whose yk label is to be determined. This is how we are going to check or test that if our learning algorithm has learned sufficiently, is able to classify that unknown or the query instance, right? Unseen example, which is not seen in the training data. So those kind of things, and that is going to be the input. The output is going to be this yk for the given xk, right? Now the classification learning algorithm, there can be any algorithm that can be like logistic regression or naive Bayes or decision tree or support vector machine or neural network or k nearest neighbor or any other, right, deep learning network. So this is for the classification problem. Same if I look at the regression problem, mostly this formulation is going to be same x1 y1, so where y1 will be nothing but a continuous value attribute, right? It will be a continuous value attribute rather than a discrete value attribute. So in classification or in regression, the difference is that the labeled data sets will consist of order pair only in both cases. But in case of classification problem, this y, that is the target label, will be a discrete variable which can have few finite number of values, whereas in case of regression problem, this will be a real number value attribute, right? It can take real numbers from some minimum to some maximum, right? And the classification algorithm, for classification problem, we are going to use a classification algorithm just like logistic regression, naive Bayes or decision tree, right? But for regression problem, we will be using regression algorithm. So regression algorithms are like linear regression, decision tree regression, SVM regression. So there are a number of regression algorithms when we try to solve a regression problem. And then your hypothesis, learning hypothesis. As I already said, this hypothesis is a function. Here we denote this function as theta of x with a set of parameters theta. So basically this function is going to be a function of a few parameters which we call as thetas, and we are going to learn these thetas as far as the learning is concerned for this algorithm. So basically what function we should learn, that is the whole point about machine learning, right? Supervised machine learning, that what function that you are going to learn. The better function that you are going to learn, the better it is going to perform for its classification or regression task, right? So this is just a again this repetition of the same slide, but now considering that it is annotated with this formal notation, that where are the x1 y1 or x2 y2 or xm y1. So we got people are keep coming. So you can see that we got this data, right? So this data, so x1, y1, so these are the x1s, x1s, x2, x3s, and this orange column is nothing but the y's, all y's, right? So these are that is your label data, and this is your s theta of x. So s theta of x is nothing but a kind of function, right? So this network represents a function of weights, right? Similarly, in a decision tree, you're going to have a decision tree, which is going to be learned, right? So we are going to learn a function, and in the mathematical sense, it is going to be a function that we are going to learn. A learn classifier will have got these weights learned, for example, in this neural network case. And when a new instance come, we know that we don't have the information about its outcome. We will pass this problem or problem instance to learn classifier, and we are going to get the output here, the predicted value corresponding to that query data. Right. So let's take an example here, right? Let's take an example. A student, let's say, since you people are familiar with this academic domain, let us assume that we are running a class, CS651 machine learning class, and we want to know that whether a student will going to fail or pass. So if we see this problem, a student will going to pass or fail, it's a classification problem. And it's a binary classification, you know that, right? Why it is binary classification? Because it has got two classes only, right? We are going to label a student with pass or fail. So it's got two outcome only. So what it is going to take as input, it is going to take as student record, maybe from the previous batches. So which student got passed and which student got failed. And a student will be represented by some feature vector. So we will know about some information about this student. For example, its CPI or its score in some other courses, or how much effort that the student has applied in that course, attendance, maybe some other variables which might have influence on this outcome. So a feature is nothing but typically should have some way like related with the outcome, with some influence on the outcome. That makes sense. Otherwise, what may happen that you may have a number of features which might not be really correlated with the outcome, and therefore these features will simply create unnecessary computation problem and probably confuse your classifier at times. So an important idea here in the machine learning problem is to know about that what features to use for solving a problem, right? This is very important and significant consideration for a successful application of machine learning, right? And another input is going to be, once we learn this classifier, then a new student data whose results to be predicted will be inputted, and we will predict the results on this student data. So we'll say that whether this student is going to pass or fail. So this is what the input part of the classification problem. Output is going to, we are going to say yes or no, so like 1 or 0 or whatever, like pass or fail, right? And the supervised machine learning, let's say algorithm, let's say we use logistic regression. Please mind that whenever we use a specific algorithm, right? Obviously, you need to use one of the classification algorithm for a classification problem, or regression algorithm for a regression problem. And there are ways of using multiple algorithms also, and combining their results in an ensemble learning approach. But let us keep our discussion simple. We can choose one of the candidate from the class of, let's say, classification algorithm, right? And logistic regression is one of the algorithm. Now, which algorithm you are going to choose? This is again an important consideration, right? So so this will depend on the given problem. And it will take some experience, right? Some good understanding, some good exposure of you in solving machine learning problems or those kind of problems, that what kind of algorithm is better suited to what kind of problems, right? This is an important consideration. There is no straightforward idea which can be learned upfront before having any experience with this machine learning. But gradually you will enjoy this, that you will be getting familiar with each of these algorithms, their strengths and weaknesses, and therefore you will be very wiseful in selecting one of the suitable algorithm for solving the problem in hand, right? And this hypothesis function in this case is going to output a value which will lie between 0 and 1. You can say it should be only 0 or 1, but let's say if your hypothesis function is a continuous function, so it produces an output between 0 and 1. So what we can do in the simple way, we can interpret that if it is less than 0.5, then we say, okay, one outcome. And if it is more than 0.5, we'll say another outcome. So this is how we can decide that how we will have this binary outcome suggested, even if the hypothesis function is generating a continuous value. It depends, right? Okay, no issue. So let me formulate this problem that whether your student is going to be fail or pass in this, right? So you can see we have got this table, which is nothing but the data set for our problem. And this data set consists of features. So this study is one feature, number of like hour of study is one feature, number of TV hours watched can be a feature, amount of WhatsApp, Facebook, or social networking, the time given to those kind of activities, maybe how much you scored in 12th or 10th, or your attendance. So you can see there can be a number of features which might have influence on your outcome. And this is not I'm not giving you just a list. You may think of some other feature variables which can also have impact on your results. Number of friends, for example, if you have more number of friends, probably you are going to score less, or maybe, I don't know, I mean, but then, yeah, one can say that, yeah, this may have some burden on the results. So those kind of things. So a good machine learning expert, what he knows is, like, he or she knows about, like, whenever he takes a problem, he needs to know about that what feature set he's going to use for solving this problem. So what features can be relevant features, so that not to miss out those important features if they can capture most of the characterization or important behavior of this problem. So this is important, okay? And you can see that there are a number of instances included. So there are like 10 or 15 or maybe 100 instances. And these instances are nothing but the data that we got from the past students. That the past student so for example, the student number 1 who studied for 20 hours, who watched TV for 21 hours, who got invested 60 hours of Facebook or WhatsApp time, social networking time, who got 78% in the 12th, 68% in the 10th, and attendance is like 68%, and got failed. I mean, just a ridiculous instance, but yeah, since it is the data, we cannot help you. I mean, we'll take the data as it is, right? So we got for a number of students, we got this data, and we got their information also, that which student got passed and which student got failed. So you got this table. It's nothing but the data set for your supervised machine learning problem. Here it is a classification problem, because our outcome is going to be pass or fail. So these two outcomes only, right? And that's why it's a classification problem. Let us assume that if we want to compute the score, then how much it is going to score, the percentage of marks. So so our result column will be changed by the percentage of marks rather than fail or pass. So if it changes with percentage of marks, then this problem is a regression problem, right? So you can see that there is not much difference between a regression problem and a classification problem. It depends the way we formulate this problem, but because of the target variable, we call this a target variable, right? These are the input variable, right? And I have already told you about other notation, this superscript with x1 and y1, x2, y2, x3, y3. These are nothing but our ordered pair or the data set. And it's a labeled data set because we know about these y's, right? So we know about these y's, and that's why this is a labeled data set. while you will learn about unsupervised machine learning problems, you'll find that they comes with the data, but their Y column will be missing. I mean, there will be no label. So they will be called as unlabeled data. So what you can do with unlabeled data is you can solve different class of problems, and that's why they fall under the category of unsupervised machine learning, not the supervised machine learning. So in this supervised machine learning, if we use this fail pass case, then we are talking about two outcomes, and it's therefore a classification problem. But if we replace this by a percentage of marks, then it will be a regression problem. I believe that this is clear for you. So our target variable or output variable or output attribute, it's if it is a real number variable, then it's a regression problem. If it is a discrete variable which can take few finite predetermined values only, then it's a classification problem. Okay. So the basic philosophy behind all these algorithms, whether it's a regression algorithm, it's a classification algorithm, is to find this function, which is nothing but given an xi, that is the xith data point, and given its solution yi, we want to know about this function. We want to compute this function, which is known as h theta here, right? So this knowing about this h theta is the all ultimate objective of your machine learning algorithm. If you reach to a situation where you say that I have learned this, I know this, my network or my function got trained, that means you got h theta learned, you got h theta known. And h theta is basically a function of theta. It's not a function of xi. Xi is fixed. I mean, inputs are fixed. You know that when you give this training data, your inputs are already known. So xi is not an input. The input for this model to learn is this theta. So you need to focus on that how to learn this theta with given inputs. So your inputs and outputs are basically considered as constant because they are already known for this problem. What is not known is this function. Okay. So generally what happened when you have this kind of formula and when you solve mathematical problem or some problems where you use some formula, what do? You know x, and you put this x, so you get an input as x and you compute y, right? Now this problem is not of that nature. Here x and y both are given, but what is not known is the theta, that is function. So once we got a number of xi yi pairs, what we try to do, we try to approximate s theta as much close as possible, which provide us the best performance, right? Maximum performance. So this is the whole philosophy behind this machine learning algorithm. It can be a regression problem. Yi can be a real value attribute, or yi can be a discrete value attribute. Okay. So can this function be learned? That is the question, right? Now the point is that since xi and yi, definitely for that xi, yi is the answer. For another xi, then another yi is the answer. So definitely there is a relationship between x and y. That is for the given problem and its solution, right? So problem and solution, problem instance and solution, problem instance, solution. So definitely there is a relationship. But can we know this relationship? And this is $1 million question. How can we know this function? Is it a square function? Is it a cubic function? Is it an exponential function? Or is it some high dimensional polynomial? Or what not? So who knows? This is a very important question, and very basic of all machine learning algorithm. How can we learn this ideally, which is probably that function is obviously there, But who knows this function? Once if you know this function, then you got the best function learned. But how would you know this function? And that is actually a problem for all machine learning algorithms. Since this function cannot be known whether it is a straight line function or it's a squared function or it's a exponential function or it's a more complex function. When once we just, since we cannot know about this and there is no way to know about it, what we do is like we hypothesize. We hypothesize a function first. What does it mean? It means that we envision, let us assume that, okay, it's an exponential function, or let's say it's a cubic polynomial function, which is probably is the function which we have to learn. So this idea of the shape of the function, what could be the shape of the function, is to be determined by us, by humans, right? By experts. That, okay, use this function and then learn the parameter of this function. You know the cubic polynomial. So let's say use x cube. So ax cube plus bx square plus cx plus d. So this is going to be the cubic polynomial, right? Now x square, x cube, these are the inputs. But what about the parameter of this function? Parameter of this function is a, b, c, d. Do you know them? Obviously, we don't know them. And that's what we need to, we want to do. We want to know about the values of a, b, c, d. Once we know this a, b, c, d, then we know this function, whole function. This is ax cube plus bx square plus cx plus d. So this is what the function that we are trying to learn, right? So what we are going to do, so each of this algorithm, whatever algorithm we use, they hypothesize a function first, right? They have to assume a function first. Obviously, the function will have some parameters, and these parameters we will learn from the data. Otherwise, the size or the shape of the function is to be first assumed. And this is a default assumption in all algorithm, and that's why each of these algorithms, they carry some bias towards the function that they assume, and that's why we say that, okay, these algorithms can be biased, and there can be variance associated with each of these algorithms because of this idea, right? So one very fundamental thing that all of you should know, that in machine learning and that to supervised machine learning, when we try to connect this input and output and try to learn a function which connect this input and output, which map this input and output, this function, there can be an ideal function, but nobody knows this. And therefore, the second best thing that we do is like we, with our expertise, with our intuition, try to think a function, okay, of some size and shape with unknown parameters. And what we try to do is, as a learning part, is like learn those parameters. Is this clear? Okay. So the different machine learning algorithm will try to learn this predefined function, a different predefined function in some sense, right? And they believe that this function can capture this mapping more closely. And that's why we have so many algorithms. Each of them can be improvised further and can be improved upon, but the idea will remain the same. And therefore, there is some bit of luck also goes in machine learning, that the function that you choose, how closely it represents that ideal unknown function. If it is close to that ideal function, which is absolutely unknown, then your algorithm is going to perform well. Otherwise, your performance will be a bit far from your expectation. Right. So let us take this linear regression problem here. That is the class of algorithm where we use linear regression. So I believe that I've told you that how supervised machine learning algorithms, they typically behave or they typically look like, right? They will try to learn a function. So what function linear regression try to learn? it tries to learn a linear function of input variable, right? So this is an example. For example, if you want to predict marks of uh, a student based on the number of hours of study, so there is only one input variable and one output variable. The marks are output variable, the number of hours of study is the input variable, and let's say all those dots, what they represent the data which is like the previous data, right? Now you got a new data which is xi, yi, and you want to predict, sorry, not yi, you want to predict, you got xi and you want to know about what should be the yi for that xi, right? So that is the problem. Yeah, this is a simple linear regression, which is the linear regression of one variable. One variable means one input variable. Output variable is mostly like it's going to be one, right? So output variable is y, which is marks. Input variable is the number of hours of study. Let's say you plot those xi, yi pairs, all those pairs. So all those pairs, when you plot, you can plot them in a 2D space, right? And you can see that all those dots are corresponding to each of these xi, yi pair. So what you are going to now, what can you learn? So this is linear regression. You can learn a function which will pass through all these points. Now, interestingly, all these points are like, yeah, somewhat distributed in the space. They're not coming in the under the same line, or even if you think about drawing a curve which will go through them, then still many of the points will be left out. So even if you try to fit a curve which try to capture the relationship between known x and y, that's not going to help here, because you will see that, okay, some of the points still will not be covered. Anyway, I'm here, what I'm trying to do is I'm trying to learn a line, equation of a line, right? A simple line which may not pass most of the points, but will try to like go as close as possible to these points, right? So how can I find this line so that this deviation, which is like all these points are deviated from this line with some margin, right? Each of these, like for example, they are deviated with some y-intercept, right? You can see here. So all these deviations should be smallest. So what should be our objective function here? That all these, so I should get a line where this deviation, that is the y-intercept of all those xi, yi's. So those y-intercepts should be as minimum as possible. So sum of all those y-intercepts should be as minimum as possible. So what I can do, I can formulate my objective function, and I can define this problem is to find a line which goes as close as possible to all those points, such that this summation of y-intercept is minimum, right? That deviation is minimum. Deviation of those points with respect to these lines. So a line, so can we find a best line? Yeah, we can find a best fit line. You can go through some literature, and that there will be a proof of this, that you can find a line which will be the best line that will fit to those points. How do you decide that this is the best line? We will decide that by computing this error nothing but the deviation, so sum of the deviations, and we will square this deviation. Why? Because some deviation is, if we see the direction, so some deviation is positive and some deviation is negative, like in one direction and the other direction. So if we take their sign, then these deviations, when combined with, when you try to add them, they will cancel out, and you will never know the amount of deviation actually. So what we do is like we square these deviation and then we sum them up. So that becomes our error functions, right? Or the cost functions. So you can see the cost function is nothing but this deviation. So what we did, this is the predicted value, this is the actual value. Okay, there is something wrong here. So that is the superscript yi is like I is the superscript of y. So you can see this difference is nothing but that y-intercept. And what we have done, we have squared it. So what we've done, like that that error, that deviation, and then we have summed it over all those m instances, right? This deviation, and just taken an average of it, right? So what we got is like, this is nothing but an error function, or also called as cost function. And what you try to do, you will try to minimize this function. So when you minimize this function is a function of theta, because different values of theta will give you different cost, right? What is theta here? So for that case, in the simple linear regression case, you don't have all these terms. You have only some just x, right? One variable. So you have theta 0, just like y equal to mx plus c. So this is your m. No, not this. This is your c, and this is your m. So mx plus c is like this same equation, but then since why we are using theta 0 and theta 1? Because when you use more attributes, not just one attribute, but many attributes, you are going to extend the same idea, and you are going to get this algorithm worked out for you, even for simple linear regression also, and for multiple linear regression also. So you will see that same equation and same kind of cost function and same kind of formulation can be used. So it's a very extensible idea. Straightforwardly, we can extend this idea, and that's why we use these thetas: theta 0, theta 1. There are many other variables also: theta 2, theta 3, theta n. So you can have n variables, n plus 1 variables, theta 0 to theta n. And you can put x0 equal to 1. So you can formulate this as a vector by taking a transpose of theta vector, theta transpose, and then x, where theta and x are, they are column vector. Theta is like theta 0, theta 1, theta 2, theta 3, so on. X is x1, x2, x3. So your s theta x is nothing but a vector. In a vector notation, it can be represented theta transpose x, which is nothing but same explanation. Yeah, here there will be x0, but x0 is already known as 1. So whether you put x0 here or no, so this is the same equation that will come out from theta transpose x. So that is your hypothesis function. It's a linear function, right? So what is the big deal here in this linear hypothesis? That we have found this linear hypothesis works very well, and you don't need a very complex hypothesis to learn. Something which is a little counterintuitive, because this is the simplest of the functions that can be learned. And in practice, it has been found that this linear regression function found to be very effective. In fact, people tried with complex expression like this complex hypothesis function, and eventually they figured out that those complex expressions makes your algorithm little overfed rather than the right fed. So it's a better idea is like to use this function. So linear regression is one of the very powerful algorithm, though very simple algorithm, but very powerful to learn those thetas and therefore learn that function. That is the hypothesis function, right? Once you know these thetas, now, and so if you know some maths, you know that if there is a function of theta, which is like yeah, this is multi-valued function, multi-variable function. So it's a variable. It's a function of theta 0 plus theta and theta 1, theta 2, theta n. So like a n plus 1 dimensional function. So when you want to minimize this cost function, this is because this is also an error function, you will be differentiating this, right? If you remember from your experience of differential calculus, there is a function of x and you want to maximize that function or you want to minimize this function. And the simple idea to minimize is to differentiate with respect to x and make it equal to 0. Since this j of theta is not a function of one variable but n plus 1 variable, so what we are going to do, we are going to differentiate it. Each time it's going to be a partial derivatives. So on first time it will be with respect to theta 0, next time it will be theta 1, next time it will be theta 2. So we are going to differentiate them every time and make all these equation as 0, and that is going to give us those theta values, all those theta 0, theta 1, theta 2, theta 3, theta n, for which this cost function is minimum. And once we reach to this point, then we say that, okay, we know about these thetas, and therefore we have learned this function, right? And that is what the learning. So this algorithm is a simple algorithm, also called as gradient descent algorithm. So what we do is, like, we start with some random values of these thetas for all those theta 0 to theta n. And what we are going to do, we are going to take update this theta at every step by a derivative of this. You know, this partial derivatives, it will give you some kind of slope, right? And some magnitude of this. And this alpha is like learning rate. So these two together will compute some values which will be in the direction of some getting deducted from this initial value of theta 0. And the same we are repeating with each theta, right? And that we will do a number of times. Now the interesting thing here is that this value, that is the reduction amount for each of these theta, its first thing is like small, and second thing is in the direction of making this cost function as smallest. This is the kind of guarantee that you get. Again, it's not very difficult to show you that why this is descending to the direction of minimizing the cost function. But this is a very important idea, that this magnitude, this value, it can be positive, it can be negative, whatever it can come out to be. Ultimately, it is going, so this updation will cause your j of theta, that is the cost function or the error function, to go down. And there is some minimum value of j of theta where our algorithm is going to converge. So what is going to happen? We are going to do this in increment, in steps, one by one. Number of steps, maybe 100, maybe 1,000, maybe 10,000 steps. We are going to update these thetas, and each updates of this theta will make your cost to go small and small. And there will be a point where their further updation will not be required, and it will not improve or reduce the cost anymore. And that will be the point where you will stop. And that will be the point where you got all those thetas known to you, and that will be the point where you will say that you learned those thetas. And that will be the point where you will say that you learned the function, hypothesis function. And that is the objective of the machine learning algorithm, that learn the hypothesis function. Once you know this function, which is y equal to s theta of x, now what will you do? You give x and you'll get y, because now you know the already s theta, right? So you got s theta of x, right? So what is y equal to x theta of x? So once you give this x, you already know now this function s theta, which is, you know, theta 0 plus theta 1 x1 plus theta 2 x2. Now you know all those thetas, and if you augment this with x, you know the right hand side, and therefore you know the y. And this y is nothing but predicted value of your y for that x. So this is how we'll get this prediction. This is an explanation that how these values, alpha, learning rate, and this partial derivative of the cost function with respect to that theta, will make this whole quantity, will make your new value of theta to be smaller. If we start somewhere here, then it will allow to go on this side. And if you start from this side, then this minus will, your gradient will be negative, so this will become positive. So you will move from this side. So whether you start from here or here, you will start randomly in the space, and the theta, this error function space, with this initial value of theta, wherever you can start. But what happened after a few number of iterations, you will reach to this point, which is nothing but the minimum value of j of theta. So very nice idea, very simple idea, which will allow you to converge. And wherever you start from left hand side, or you can start from right hand side, you will be descending, and that's why the name of this gradient descent. In this algorithm, your algorithm descent along the gradient gradually, and with some carefulness, you can make it converge to this point, which is the point of least error, right? Least j of theta. Similarly, we have another algorithm, but now this algorithm, which is called logistic regression, is a classification algorithm rather than a regression algorithm. So sometimes it may appear as a misnomer that this is a regression algorithm, but it's basically a classification algorithm, not a regression algorithm. Why regression is used? Because it's an extension of linear regression algorithm only. Only thing is the output of the regression, which is a continuous value attribute, is converted into a binary attribute, that is 0 and 1, or the values which will lie between 0 and 1. So this regression, which is otherwise linear regression, when applied with a logistic function, will map this minus infinity to plus infinity values, all those values, to a range between 0 to 1. And when it does this, and that's why we say that that's a logistic functions that is applied to this regression problem. It's a linear regression problem, and that's why the name of this algorithm is logistic regression, where we get output which lies between 0 and 1. Since it is a continuous value which lies between 0 and 1, with a simple idea that if it is less than 0.5, we'll output 0, and if it is more than or equal to 0.5, we'll output 1. So we can binarize our output by some assumptions, and this is how we can start classifying the output as a binary classification task. So this is the logistic function. What it takes is, like, you see, Z is nothing but those theta transpose X, which is nothing but a function of the linear regression. You apply a logistic function here, and that's why your hypothesis function is a little change. It apply a logistic function to this linear regression function, and that's why the output will now lie. This function will vary from 0 to 1. You can see 0 to 1. It goes from 0 to 1, and you can see at this point it's like 0.5. So we can say that if it is less than 0.5, it lies this term. We will say, okay, the output is 0, and if it is more than 0.5, we'll say that, okay, so we'll output as 1. So we are going to binarize. We are going to interpret this as 0 and 1 in a very simple way. Only difference between linear regression and logistic regression is, like, it's a cost function a little more, and there is an idea here to make this cost function as a convex function. If we could have used the same cost function as of that linear regression, then that will turn out to be a non-convex function, and therefore that may have multiple minima. We want a global minima, so we want a convex function which will have a single global minima, so that there is no stuck in between. And some of you who know that, like, local minima and global minima kind of things, where probably you might have gone through AI search problems where you perform heuristic search, and you know that we encounter those kind of things. Is it like local search or local minima or global minima? So similar things, like a function can have multiple minima but if it has multiple minima, then our gradient descent can stuck on a local minima. So for that reason, we use a little more complex cost function. But the advantage of this cost function is to ensure that we got a cost function which is convex. And this convex function will allow you to reach to the global minima, and therefore the least error possible. So that is what we can do. Like, so for these two algorithms, whether it's a linear regression or logistic regression, whether we use linear regression for regression problem or logistic regression for classification problem, one thing is for sure, that you can solve this problem with the best of these algorithms capabilities. You can fine tune this algorithm to the best of their nature, though they can still provide some error, but you cannot improve further as far as their algorithm capabilities are concerned. You have to do some other arrangements, like doing some regularization or reducing some overfitting by some other means, or underfitting if it is underfit algorithm. But whatever, the point is, like, since we got the cost function as the convex function, which has got only one minima, and if you fine tune your gradient descent algorithm to descend gradually and do not overshoot it, do not diverge. So there are ways of doing it. I mean, you will take some time to understand that how to get your gradient descent algorithm converged correctly. But once it converges, it will give you the best possible results for that algorithm. Okay. Else the two algorithms are mostly same, right? There is an extension of like this idea, the logistic unit, and you will find that we can take it to and conceptualize our neural networks where there are more than one logistic unit is used. So when you are using one logistic unit, it's logistic regression. But when you use a network of logistic units or different kind of units, and the idea will remain the same, you will have a neural network, right? There's one thing which I would like to say very quickly is, like, we got from this logistic regression algorithm, we got a binary classification, either 0 or 1. How would you do a multi-class classification algorithm? And the idea is very simple, that if you have multiple classes, you can apply this idea which is called one versus all. So you consider one class as one type and all other the instances of all other classes as the second type. So the multi-class classification problem can be modeled as multiple binary class classification problem, one for each class. And this is how you can compute these values, which will be nothing but will come out between 0 and 1. As you know, that logistic unit will give you a value which will range between 0 and 1. And out of this, like, let's say if it's a 10 class classification problem, that means it will be converted into 10 binary classification problem. And each of this is going to give you one value, right, which will lie between 0 to 1. Now, whichever is giving me the highest, I'm going to apply that. I'm going to assign that class. This is a very simple, like, idea to figure out that which class this instance is going to belong to. So that is how we can extend the idea of binary classification to solve this problem of multi-class classification. Right. Okay. So yeah, conceptually it is given here. So one is like, so for example, you're considering triangles, then all other classes will be circles. Then the next case, like rectangles or crosses. You can see the all other classes we consider. So each of this is looking like as a binary classification problem. You can train a classifier. Its classifier will give you a h theta of x, that is the hypothesis function, which will range between 0 and 1. And whichever provide the close to 1, like highest value, we are going to assign that particular class. Right. I'll skip this part, which was nothing but meant for extending the idea of logistic regression and take it to neural network. But I hope that this will be taken care of by somebody here. And then taking it to even further, more complex neural networks, including deep neural networks. So there is a definite connection between logistic regression, neural network, and deep neural network. Logistic regression you can consider as like the simplest of the classifier, and very effective classifiers when we have like simple problems to classify, right? Maybe binary classification problems can be effectively classified. But when you go for higher classification, you can use logistic regression unit and logistic units in some network form, and that is how you are going to come up with a more complex, like functions that can be learned using neural network, and even more complex using deep neural network, where you can have even higher number of layers of these units can be placed. So the number of layers may be even more than many more than in neural network. So deep neural network are like again extension of neural network, and I hope that somebody will cover that. Regarding the supervised machine learning algorithm, as I said, there are two classes of algorithms. One is regression algorithm, classification algorithm. In the regression algorithm, we have discussed simple linear regression and multiple linear regression, right? So these two, simple linear is like linear regression of one variable, and multiple linear regression is linear regression of multiple variables, multiple input variables, right? And then there are more advanced algorithm like ridge regression, lasso regression, and then KNN algorithm, which is also can be act as a classification algorithm. So we can formulate KNN as a classification algorithm as well as a regression algorithm. And similarly, it goes with decision tree algorithm or SVM algorithms or night based. So any algorithm in that sense can be formulated either as a regression learning for a regression learning problems or a classification learning problem. There are a number of open source tools. Some of you, if you are already in this field, you know that, and these are all open source, so that's why I have kept them, right? For example, Keras, like people who are using some sophisticated deep learning solution, they are using Keras, or TensorFlows like from Google. So you can see like and scikit-learn, sklearn kind of libraries. These are all libraries basically which you can plug in your uh, let's say Python programming. It is highly recommended that if you can do using Python programming, and these libraries can be used. So your programs will not be large program, and you can also use some work which is already uh, developed for you. So you can use those functions and code and can quickly develop your algorithms, right? Coming to this COVID-19, yeah, interpretable modality prediction problem, which is like just published. You can see like these people, they did a very simple task, and it's not a very complicated stuff. They got a database of blood samples uh, from 485 infected patients in the region of Wuhan, China. And they have extracted a number of like 35 parameters from this blood samples. And then using some these techniques, machine learning techniques, that they identify that there are 3 biomarkers that predict the mortality of individual patient more than 10 days. I mean, they will live more than 10 days in advance with more than 90% accuracy. So you can see, and they have given the name of this biomarker, for example, LDH or lymphocyte or high sensitivity secretive protein. So those kind of things, so they have identified that. And what they suggest that, okay, when if you diagnose the patient with this kind of situation much before, then you can actually give them treatment which is more suitable to reduce those kind of things, right? So in that sense, it can help us to reduce the mortality as well as a right kind of treatment that can be given to those patients. So you can see like this, you need a data set here to figure out these kind of relations and connections and the usefulness of this useful information that can be inferred from this data set. There are many other things that you can do with the COVID-19. Just look for these links which are given. So for example, Kaggle that is hosting a number of competitions and also like sharing the data, which is like COVID-19 data obtained from various sources. You may not get a very big data at this point of time, but yes, whatever data you can get, you can quickly do some kind of analytics and apply machine learning techniques and can come up with some useful conclusions, and that can be published, and that can help people to like deal with this COVID-19, right? So thank you very much for your patient hearing. I'm really thankful that so many of you and have so much of patience, like around like 2 hours that I discussed about like this introductory part of machine learning. Now I can take your questions, and whoever would like to ask, unmute their mic, ask the question, and then mute your mic again. Thank you very much.
Dear participants, you can also write your query in chat box. I am enabling it for you. And also, so many participants have raised their hands since long, so I'm taking them one by one. So there is M. Sahu. Yeah, you can ask, sir. Hello?
Yes, please.
Someone, Miss M. Sahu is there? I have unmuted you. Please, you can ask. You have raised your hand. Okay.
Yeah, somebody else is.
Shipra Goyal.
Hello.
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 Haji.
Sir, where we can find the COVID-19 data, real-time data.
So I have provided you a couple of links here,
Okay.
right? So, and you can also visit WHO site. They are also like sharing some data which they got from different countries.
Mm-hmm.
It's a really high time and a good time that you can quickly go through those data and you do apply some machine learning and frame some objective for what you are going to like solve this problem, use this data set and get the kind of information from this data set. But that can be very useful information and it's a very yeah, a prospective time for publication. So whatever like results, there will be initial results and they will be published very soon. You can see like the paper that has been published. It's a very small study, and they have used a dysentery algorithm, which is a very elementary algorithm also.
Elementary algorithm, yes.
Yes, and they got they published in the Nature, I mean, Journal of machine learning of the Nature publication. So that's a very fantastic publication they got from this very simple and small study.
Okay. Thank you, sir.
Okay.
Thank
Yeah, please go ahead. Any next?
Next, someone Bima Raju is there. Yeah, you can ask your question. Hello.
Yeah, you can go ahead if somebody is not.
Okay,
So
someone Rupa Patel is there. I'm unmuting. Rupa Patel, you there? No. Anil Kumar. Mr. Anil Kumar, you there?
Hello, very good afternoon, sir.
yeah, Anil, please tell me.
Yeah, I have enjoyed your session, sir. You have started from the scratch and leads to the final implementation till gradation. Very nice and blessed to hear you, sir. Thank you so much, sir.
Thank you, Anil, for your kind words. Please.
Sir, my query is that, sir, suppose I am solving a problem for air quality prediction, air pollution.
Okay.
So suppose there are three labeled target classes, let's say class A, B, C, representing mild, moderate, and severe type of air pollution.
Right.
So, sir, whether this class of problem falls under regression or classification, sir?
It's a classification because you have identified the classes.
Yes, sir.
Only thing is when you will be dealing with the features, and those features is nothing but those inputs that you will take from like maybe the amount of some particles or whatever, like those kind of inputs. Then the classifier that you're going to use, and they are going to provide you output as maybe again a real number in some sense, right? Or a probability of something. Then you have to interpret these probabilities, and you have to see that if they fall under these three categories, right? So you have to group them and ensure that you are correctly classifying. Otherwise, it's a classification problem.
Classification, we are doing forecasting, sir. So it may be possible, sir, more than two classes are there.
Yeah, definitely. A multi-class classification that I discussed at towards the
Okay,
end.
okay.
It's
I
nothing
have
but
got, sir.
it's nothing but an extension of binary classification, where
Sir,
you can.
if you allow
Yeah,
one
yeah,
more
please.
query, sir, please. One more query,
Yeah,
sir,
please.
please.
Please,
Sir,
please go ahead.
is there any thumb rule, sir, to decide the number of hidden layers in the neural network model? How many layers would be there?
Not really. I mean, regarding the thumb rule, is like people try. So it's a more of like trial and error approach. See, what
Okay.
happened, I can provide a rationale behind this. What happened that when you use this neural network with more number of layers, your hypothesis function, which we have discussed, that becomes very complex, very complex. And it becomes so complex that it is very difficult to intuitively understand that if we increase the number of layers, whether it is going to help or if we reduce it. So the only way by which people do that is they experiment it with different number of layers or the different number of nodes in each layer. There are some heuristics advice which is given depending upon the type of data set that you use, and that you can like figure out from some papers, some articles which might suggest you that how to choose these. But these are more of heuristics rather than uh, kind of targeted answers.
Okay, no fixed rule means, sir.
No
Just
fixed.
hit and trial method. Okay,
Yes,
okay,
yes.
fine.
No.
Thank you, sir. Thank you.
Vikram Gupta.
Yes, ma'am.
Yeah, you can
Uh,
ask your query.
Sir, very good afternoon. Sir, you have given so many problems and so many examples and live examples also. And I have been very, uh, I'm interested to know, sir, whether we should know all the theoretical portion like linear regression or something else in detail,
No,
or
no, no,
whether
no.
we can use all the inbuilt functions in a programming language for solving these.
So there are two things, right? So if you want to become a machine learning expert, in the
Yeah.
sense that you understand what is going on within the algorithm, how
Okay.
algorithm is working better or not performing as per the expectation. If you want to go into those kind of details, right, then you should probably learn these algorithms so that you can characterize, you can play around with their properties and their characters, and then you can fine tune them. But if you just want to use them for the as a user, as to apply and solve some problem, then many people, they do some trial and error, and some things may work for them and something may not work for them. They may probably understand this or may not understand it, but then they can solve this problem. So it's all about like your objectives, where you would like to put your effort. Obviously, when you will go into more details, you will require some a lot of effort to understand the interplay between this like this hypothesis function, that is the input and output relationship. So, and how what kind of hypothesis function is better suited, and how to fine tune that hypothesis function. So if you want to learn this hypothesis function and its influence or its fine tuning, obviously you need to go in the detail. But if you don't want to do, and you just want to apply it and for experiment it, and you are ready to give some time for experimenting it, some probably after some experiments you may get a good solution, which probably will not provide you insight, but yeah, providing good results.
Thank you so much, sir. You are awesome.
No, thank you very much for your
Thank
kind
you.
words. Yes.
Next, Prakash GL.
Good
You there?
afternoon, sir. Yes. Good
Yeah,
afternoon,
Prakash.
sir. Good afternoon, sir.
Good afternoon, Prakash.
Sir, I have query in gradient descent algorithm cost function.
Oh, good.
if you go back to that slide, I can point out that linear regression.
Yeah, so this is the gradient descent.
Previous slide.
Okay.
Previous slide, sir. Again, previous slide. Previous.
This one.
Again, previous. Cost function.
Cost function.
Gradient descent algorithm cost function. Next. There is a this one, sir. Here theta 1, we are updating the thetas.
Right.
So 1 by 2m is there here. Theta 1 minus alpha into 1 by 2m.
Yes.
So in theta 0, 1 by m is there.
Right.
So the variable, it varies for all the thetas, or it's constant, sir?
No, just repeat your question. I just lost this.
No, in the partial derivative algorithm.
This is the algorithm, right? Yes.
Theta 0 equals to theta 0 minus alpha into 1 by m.
Yes.
Then the error, target output and actual output.
Right.
Theta 1 equals to theta 1 minus alpha.
Right.
Into 1 by 2m is there.
Oh, in the next okay, next line.
No, here 1 by 2m is a formula is varying the coefficients. Theta 0 is 1 by m, theta 1 is 1 by 2m.
So are you asking why this 2 here and why this?
Why
is it?
2m is a mistake or is actual formula, sir?
Actually, the formula is see. This important whether you have 2 in the denominator or if you don't have 2, this doesn't matter. What happened that when you will differentiate, just remember the differentiation, that it's a square function, right?
Okay.
So that when you differentiate, then you know that when we differentiate a square function, then it will be, if it is x square, then it will be like 2x. So
correct.
the 2 will come here, and then this 2 will be cancelled. So that's why because this is just a constant stuff, the algorithm doesn't depend on this, whether you have 2 or you don't have 2. So it's not going to influence so it's the only thing is like to make your calculation simple, right?
Okay.
So you don't have to every time multiply or divide by 2. So you can reduce some operation. Still, the algorithm remains the same.
Okay. So second question.
Yes, please.
So in a data set, so we'll have n number of dependent variable. Independent. In a data set, we have n number of independent variables.
Yes.
So how to decide which independent variable is more suits to get our target variable?
So are you saying that you got already a set of independent variable?
Yes.
And then your task is to choose which one of them to use for your problem. Is it?
Yes.
So that is a good question, interesting question. And many times we come across those kind of situation where we got a number. So one thing is, like, since it's a machine learning problem and we don't know who. See, first thing is, if we know about upfront some way that this particular variable is unlikely have influence on the output variable. If we know this, then we can take a call there. But if you don't know that out of these, let's say there are 1,000 variables, and you are not sure that which one is relevant and which one is not relevant. So there are many ways of like handling this situation. One thing is there is a whole area which is called dimensionality reduction. So what it does is like, given your problem in its basic nature, very basic nature, with all those 1,000 attributes, it will take all of them and will do some kind of analysis. For example, one is like PCA, principal component analysis, and it will reduce the number of input variables to some small number, right? There are other ways also. One thing is like what you can do is like you run this algorithm with all the variable considered at the first time, right? And see the performance of the resulting algorithm. Now what you do is like leave one out. So what you do is like you take one of the attribute and remove that, right? And then run it again. So if your performance improves, that means you or remain the same. That means you have removed a unnecessary attribute, and you can keep on doing this for a number of time. I mean, to whatever time you would like to. Maybe you can exercise all the variables, and till a point where if you remove a variable and it results in decrease in performance, you can keep it continue. You can continue to keep that variable.
It will take more time complexity.
No. It's just a it's like you can say offline experiment.
Okay, fine.
Yeah, that will allow you to just know about which are useful. Once you got that set of or subset of these variables, now you start fresh.
Thank you, sir. Thank you very much.
Okay.
Next, we are taking Vikas Kumar Garg.
Hello, sir.
Hello, Vikas.
Sir, my question is in starting you have said that mapping is done when we extract the features. So how this mapping will work? Is it the same that will work in MapReduce in Hadoop, or it is a different?
So here this mapping is it is. I think. Are you able to see your slides?
Yes, sir. Yes, sir.
So we have typical function which is y equal to fx, right? So
yes,
in mathematics, we try to connect these two things. Y is the output variable, x is the input variable, and we try to connect this x and y with a function. This is how we identify a function, right?
Mean there is a key and value pair, sir?
I would not say key and value pair because key and value pairs are and it's not a function because they are defined for certain keys only. Not a.
So how would you, sir? So how would you recognize the same field? Suppose there are 5 same field. So can we get all the 5 fields in the same key or in the same mapper? Suppose there is a 5A alphabets are there. Can we get that all 5 in the same key or in the same group?
No, I still didn't get your problem. Are your problem related to Hadoop only, or you are, asking a question on machine learning?
No, sir, and machine learning.
So machine learning, so still, you have to reformulate your question. I think you are more of like influenced by that idea of Hadoop. So here there is no key value pair. It's if you are saying that x and y are nothing but there is some so x is key and y is value. Are you taking this in that form?
Yes, sir. Yes, sir.
So there are so you got a number of pairs x and y, and you are calling that as a key value pair, right?
Yes, sir.
Now this sounds interesting. Now what you want that from a number of key value pairs that we already know, if let's say there is a new key, can I get a value for the corresponding that key? Isn't that?
Yes, sir. Yes, sir.
So
means
yes.
How can I get the
Yes, please complete.
So suppose there is a key, how can get the exact solution for that particular key?
Yeah, so that is a problem. If you are talking about, I will not compromise like a 95% or 99% close answer. I need a 100% answer. So machine learning will not help you.
Fine, sir. Fine. Means the exact solution we can find with particular key, with respect to that key.
See, for exact solution, you have to apply deterministic techniques, which is we call as traditional technique, right? So these are the techniques which where what we are trying to do कि जो की वैल्यू पेयर जो ऑलरेडी आपके पास पहले से हैं उनसे हम कुछ मैपिंग निकालना चाह रहे हैं कि कैसे कोई की को वैल्यू में कन्वर्ट होता है। तो मतलब उसके पीछे का लॉजिक क्या है, मतलब क्या कोई फंक्शन है इस तरीके का विच takes this key and give me a value, right?
Fine, sir. Fine.
हाँ, लेकिन जो मैथमेटिकल की वैल्यू पेयर प्रॉब्लम होती हैं वो that is not governed by any mathematics. Otherwise, you won't be storing that key value. You simply will be using that formula to get value against that key, right?
Fine, sir. Fine.
So it's a
Thank you, sir.
In that sense, it's a different problem than finding a value against that key. But if you are ready to compromise, if you are ready to get a key which is close enough, and you're not forcing for an exact value, then this can provide you a solution.
Fine, sir. Means this is.
So next we are taking Manjula's question. Manjula, you there?
Yes, ma'am.
Yeah, you can ask.
Yeah, Manjula?
Hello?
Hello.
Miss Manjula, you there?
So take some next.
Other, yeah.
Yes. Yes, ma'am. This is Manjula.
Yeah, you can ask your query. You have raised
Hello.
your hand, no?
Yeah. I'm asking, ma'am. Yeah. Hello, sir.
Yes, hello.
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 Yeah, sir. How alpha learning rate, sir? How the alpha
Yes.
learning rate will affect the gradient descent algorithm?
Yes, so that is a very standard question.
Sir,
Good
sir,
question.
the alpha learning rate, how it affects the gradient descent algorithm, sir?
Okay.
Hello.
Let me answer that. But before that,
hello.
Are you getting my voice? Hello.
Hello.
Are you getting my voice?
Is it a constant value, or have to choose, or have to calculate?
This is a constant value, but then you have to choose which value you are going to assign it. So that is to be decided by ourselves. I mean, we decide this, that what we are going to put, alpha equal to 0.01 or 0.001 or 0.1. So that is what we are going to decide. See this. Hello, are you able to hear me? Manjula?
I think some connection issues are there. So can we take another query, sir?
No, so let me answer this question for if somebody else is interested in this question.
Sure.
That this alpha, we have to choose in such a way so that we should be gradually, I mean, our algorithm should be gradually moving towards the minimum, global minimum, that the minimum cost function value. It should not take large steps. Otherwise, it may be the case that it may overshoot that minimum point, or it may not be that small that it is taking a lot of time to converge. So it takes some experimentation to understand that for a given problem, what should be the value of alpha. I cannot say simply that it should be 0.01 or 0.1 or 0.001, but typically people experiment it by starting 0.001 and keeping 0.01 and then 0.01, 0.1, and then moving in between a value they may find suitable, maybe close to 0.01, which may lies 0.01 and 0.1. Yeah, please. दीपशिका, आपका माइक म्यूट है.
Yes, sir. Rahul Sharma. Rahul, you there?
Yeah, ma'am.
Yes.
Good afternoon, sir.
Good afternoon, Royal.
First of all, thank you, sir, for a very good presentation. I have two small questions.
Please.
Given the data set, we split the data set into training and validation data. Is there any thumb rule? Which of standard which gives us the ratio with which we can split?
So the thumb rule is 80-20. That 80% you should use in the training, and for the remaining 20% you should be using in the testing. And generally, when we do this, we repeat it number of times. We repeat this a number of times, maybe 10 times, maybe 100 times. So we rerun this every time. What we are going to do, we are going to randomly select 80%, or you can say 20%, and remaining 80% should be used for training. And the trained classifier should be then used for the classification task. You get an answer, some performance from one. This is first set. Then you again do this same thing. So you can do it 10 times or maybe 100 times, and then finally we'll take an average of it.
Okay, thank you, sir. So one more question.
Yeah, please.
I have a small data set. We all know that in order to train machines, we need huge data sets, large data sets. But given a small data set, suppose I have a small data set and I do augmentation of that data.
Okay. Your voice is getting broken.
Rahul, yeah, he disconnected. So participants, last two queries, as time is not permitting us to take more queries. So I'm just taking two more query from Manish Ahirwar. Yes, you there, Manish? Someone with the name SG. I'm unable to. Voice is not connected. Someone with the name iPad.
They should keep their name correct.
Yeah.
Hello.
Hello.
Yes, sir. Am I audible?
Yes.
Yeah. Who is there?
Sir, this is Neeta Nathani. Actually, this is not my ID. I'm using it from someone else.
Okay.
So I have a question. Okay, sir, can you cite a practical example of reinforcement learning?
Okay. So it seems like you are interested in reinforcement learning, right?
No. Because
so there's a lots of example in the game, like game learning, where, for example, you try to learn a board game, right? So you try to make a move, and then the other person, and then so what will happen that there will be two instances of program. They are going to play with each other. So one is making move, the other is making move, or maybe there is one instance of program and there is one expert, right? So this program initially is not trained. So this program simply knows how to make legitimate move, but which move to make, this program is not aware of. Like, so it will make some random move initially, right? And what will happen eventually? This game will end somewhere, and where this program is going to lose this game, right? Because this program is not a learned program, right? So what happened that you got a reward, but then towards the end of this program, that you lost your game. So what you are going to do? You are going to discount your each of these move which you have made a little less, that because they have eventually allowed you to move to lose your game. So what eventually going to happen? You're going to play it again, and then the next time you are not going to select that move, because you know that when you selected that move, you got lost, right? So you are going to take some other moves, but this time also you're going to lose probably. So initially when you're going to play, you're going to lose, but maybe sometimes you may survive a little more in the game, and sometimes you will be quickly lost. So you are going to assign for all your moves for that game some discount. It can be a positive one, it can be a negative one, depending upon the kind of outcome, or it can be in between, right? So gradually, when you will come to know that there are some moves which are, I mean, really bad, some move are bad, and some maybe, let's say, a better move. So you will start playing those better moves, and gradually, among the better move, and you can see like maybe 1,000 times and maybe 10,000 times after that, you will learn that game, because you have figured out that what moves have made you lose or lost quickly. So you see, you don't have the data up front to learn something, but you are learning by making mistakes. So just like a small kid, when the kid is crawling, and when it start like standing up and start walking, so what happened that this kid is getting fall down more often, right? As soon as it's try to stand up, it will fall, then it will start, it will again try. So this kid has got those idea that I did balance last time when I got down. I made some little mistake, right, on that side. So try to adjust in some other way. And after a few adjustment, after a few trial and error, the kid learned that, okay, now this is the more like balanced way of like getting up. So you see, this is how these programs or this learning mechanism, they work, that you do it, and initially you are going to yeah, get worse results, obviously. But then since it is at the time of learning, so you will simply record them and will learn more and more about the better moves. So gradually, because of the better rewards, you will learn both those better moves. You will capitalize on those better moves, and a time will come when you will start recognizing that what are the better move or best move out of the moves possible. So that is how you will learn. Yes.
So the last question of this session we are taking from Sage Ruchi. You there? Sage Ruchi. Okay. So last, Shraddha. Shraddha, you there?
So what I suggest, Dr. Deepshika,
Yes,
if
sir.
there are more questions and people are interested, you can compile all those questions and can send it to me.
Yes, sir. Chat is already saved. I'll send it to you.
So in
And
the form of questions, if you can send me
yeah,
with
sure.
specific questions, so that I can type those questions and can provide a response.
Yeah. All the participants may also have noted down your email ID, so they can also contact in future if they need.
Yeah.
And all the participants, if you are having any query, you can post it in the chat box. We'll send it to the sir, and all your queries will be answered for sure. So thank you very much, sir, for sharing your valuable insight on the topic. And I really love the how patiently you answered all the queries.
No, not
And
an
thank you
issue.
very much, sir, for joining us.
It's our job, and only thing is like people, if the people are interested, and if we can get some query answered and can help in some way, that's a privilege to us. Thank you.
Thank you so much, sir. Shukla, sir, you would like to say something?
हाँ मुझे भी थैंक्स कहना है गुप्ता सर को.
Dr. Rajesh, you know, because of you only, like this, you conceptualize this program.
In fact, I should say, sir, that because of you, this FTP has been conducted. I just share the idea with you, and you immediately confirmed your participation as a speaker in this program. Therefore, I planned this event. So I must be thankful to you, sir. You have motivated us to conduct this FDP, and it eventually is going to happen now. So thank you.
Anytime, I mean, people are interested. The only thing is like we should be doing useful exercises, sensible exercises, which make some sense or become useful to some the participants, even not all the participants. So whenever such a situation is there, I'm always interested.
It is your motivation, sir, that we discussed with the team members, Dr. Deepsika and Arun Gapate, and ultimately we planned this event and floated. And almost 1,300 participants have registered till yesterday, 11:30 p.m. And the highest figure we have observed is almost 600 participants have attended today's session. So it is really a marvelous participation by all, sir. So thank you so much. Thank you so much, sir.
Thank you. Thank you. Let's disconnect and let's.
Yes, thank you, sir.
Yeah.
Thank you so much, sir. Thank you all the participants for patiently listening to us and joining with us. All the further information will be given in the WhatsApp group. Thank you so much.